So as mentioned, this is going to be the first in a series. Today we're going to focus on new opportunities for applying AI technologies, artificial intelligence technologies to traffic optimization. And we've got some unprecedented situations right now that make AI tools extremely valuable and in a sense can solve problems that only AI can solve. We're going to look at some practical examples of harnessing AI to resolve traffic signal timing compromises, because the current state of affairs with managing traffic is largely based on compromise because of the underlying technologies. The agenda today, we're going to look at the AI landscape. Been massive changes that you may have noticed or not noticed, and our world is being morphed and made better for the most part by AI. We're going to look at the impact of this COVID and hopefully very, very soon the post-COVID world on the impacts on traffic operations. Traffic operations are typically based upon assumptions and observations and predictable linear growth. With this new, we have really no idea how traffic is going to look next week, next month, next year. So some of the fundamental assumptions and tools we've been using are simply not going to be effective. We're going to look at typical challenges of very specific types of things that are challenging to manage from a traffic engineering standpoint, and see how, and look how AI can resolve those typical challenges and compromises. And we'll have a summary, and then, well, of course, we'll get back to questions, and hopefully have a whole bunch of questions toward the end. Or if I've done my job, we'll have none. So as mentioned, AI is transforming all aspects of our lives. So one really good example is flight. So the dawn of modern commercialized flight was really with McDonnell Douglas DC-3 around 1939, 1940. And this is typically what this cockpit looked like. So if you had to operate one of these machines, really it required a pilot and a co-pilot, also a flight engineer to manage and give hypervigilance to all these instruments to simply get you from the city of Pittsburgh to Chicago without having to take a unexpected bath in Lake Michigan. So very, very challenging environment. Even back then, they gave some really good advice. See the no smoking sign? I think they should carry it forward to the future, to where we are right now, the current state of affairs with the Airbus A350. This aircraft can take off from New York by itself, fly 9,500 miles, land in Singapore by itself, with very minimal intervention, minimal to no intervention from the pilot. So the AI has made all this possible. It's made the cost and the efficiencies and the safety so much better, and it's made the world accessible. And I'm sure many of those on this call are looking forward to being able to safely get back onto one of these vehicles and fly to our destinations. Agriculture has been extremely transformed from this typical low output, high resource consumption model with really low value, low nutrient contents, to very high outputs of highly nutritious fruits and vegetables with minimal water usage and resource usage. Probably one of the areas that's the most beneficial and most visible these days is medicine, where we've gone from this environment using very crude tools for diagnostics and invasive techniques to things like Zebra Medical has released an AI-based platform that lets radiologists get very quick and rapid determinations about lung cancers, for example. So these types of systems can capture 40% more accuracy than a radiologist sitting there. It makes them much more productive. And then we've got techniques for minimally invasive surgery with the Da Vinci system. This system can literally do operations the other side of the planet with a surgeon sitting there and doing work. So just phenomenal transformations. So the question we have is, can AI go too far? And I say yes, and I am not talking about Skynet and robotic killers on the battlefields. I'm talking about something truly terrifying, the AI-based washing machine. There are actually washing machines now that can sense the fabric types in each load. So for me, that means my washing machine and my wife are going to yell at me for mixing the lights and darks, to the nearly absurd, which is the Internet of Pets. And a slight disconnection. So technology for technology's sake, what I want to know is how this little guy got the patch cables to hack into these doors. But let's go back to traffic control. So the modern traffic control started really with the dawn of the Industrial Revolution, where it made sense to mechanize repetitive tasks. So the advent of the traffic controller started with this electromechanical traffic signal timer. And what this does is it has the dial goes around, and that's a cycle length, and there are pins, they're the offsets that change the lights at predetermined times. And if you want to do coordination along a corridor with this kind of a model, you offset these controllers, these dials to make traffic run. And that's how traffic was moved, because the fundamental assumptions were traffic was going to look the same, it was going to act the same, and that I could predict what was going to happen on a regular basis. And since that device has morphed into the electromechanical traffic signal timer with electronic makeover. So all current modern traffic signal controllers still operate under the same model of fixed timing plans, fixed cycle lengths with fixed splits. Certainly there's intelligence in here where I can do things like skip specific phases, but essentially these act like fixed timing electromechanical timers that are based upon assumptions of moving traffic, and we're going to get to those particular assumptions in a couple of minutes in a methodology for doing that. Traffic signal control is one of the last high impact domains with problems and compromises that can only be solved by the use of artificial intelligence. So those of you in the traffic engineering industry, I'm going to oversimplify this process, but this is typically how we deal with traffic issues and move traffic today. Someone goes out, or a system goes out and does a manual traffic count. It typically looks at maybe a 12-hour window, looks at the peak periods, makes some assumptions about that. That data is put into a software package that generates timing plans, either manually or automated, and that's loaded into a traffic signal controller, which is put out at the intersection to drive the lights. And there are things like detection, inductive loops, and even sophisticated things like traffic cameras, which emulate these loops. So this whole process is based on a thrice removed observation of what's happening with traffic. And this model worked fairly well up to the point where things stayed relatively the same. In this new world that we're in, we have no idea how things are going to look next Tuesday or 2 months from now. And the fundamental assumptions about how traffic are going to move may no longer be valid. So what I want to do is I want to take a moment and thank traffic engineers everywhere, because I think they've done a remarkable job with the tools that they have. Because think about this process, having to go through either in a manual or automated process to use just these simple tools to move traffic in New York City or along large arterials, or you're in your hometown with a lot of complexities and interdependencies. And the reality, sobering reality, is this unprecedented change in traffic is showing us there's really no clear deflection point. Traffic patterns are increasing, but are they different? Are we going to have AM peaks anymore? Will people go from their homes to office buildings? Will they go into major cities for events? Will the highway volumes change? So all these unknowns make those traditional models really no longer effective. And the fundamental assumptions, again, about traffic is typically based on some sort of growth, linear growth, single, double-digit growth. So we take a look at the traditional process that's prescribed by the Federal Highway Administration, US DOT. There's a fairly rigorous process to this. So starting out with, I need to solve a traffic signal particular issue. I scope the project, and right away I start dealing with compromises. So for example, with the traditional traffic timer, you have to come up with your primary performance measures that you want to measure against. Is that delay on a corridor, or is that side street delay, or do I reduce the number of stops? As you start adding complexities, this whole arena of how many timing plans do I need comes into play. And again, will these timing plans be effective? Because they're based upon the assumptions from the past. And moving through the process, you do a study, you take counts, and then you decide, well, can my actual systems and signal systems support the types of things I want to do, advanced things like with detection, what have you. So there's a very manual process to this, and the process sorts down through generating timing plans, again, based upon some fundamental assumptions that were made at some time ago, could be 2 days, 2 months, 2 years past, deploying them out in the traffic signal controller. And then the flow prescribes going back and make fine-tuning adjustments to that. So does that seem like that works in a variable environment with high complexities? Likely not. So we submit there's a better way to do this. Using artificial intelligence, you're able to simulate, really take the best and brightest traffic engineers and traffic planners that you have, and take their knowledge and their logic and put into algorithms that can drive traffic signals without having to go through these manual processes. So we submit there's a much better way to do this, starting with a very intelligent sensor at the edge that's able to classify the user types, the approach speeds, everything from pedestrians to cars to scooters, and then take that and create an image of what the reality is right now at this specific intersection. So are there vehicles waiting? Are there vehicles approaching? Are there pedestrians coming? Taking that information and plugging into this AI realm of a optimization engine. The optimization engine that we are currently deploying uses deep learning artificial intelligence techniques, which really simulate the function of the human brain. And it's really interesting because neuroscience and the latest experiments show that all human perception and cognition is actually based on simulations. So we have a biomass-based simulator of taking, we have a worldview, and this is the way AI works. This takes a worldview, so sensors would take a look at the environment around me in real time, the way that the human does. I take inputs, and then my worldview continues to be modified, and my reactions to that continue to be modified by what's actually happening right now. And deep learning AI lets us do the same thing with traffic signals. So from a local data standpoint, I have this perception and reality of what's actually happening from moving objects and robo users to stationary objects. I'm able to factor in global data like platoons approaching. So think about this again. I have the smartest traffic engineer I could possibly get who is omniscient and can see everything around me in a city or in a grid or an arterial. Taking all that data and then using policies. So instead of having to go through the rigor of selecting what are the compromises that I have to go through using a policy-driven engine, and I'm going to get back to this in a couple of minutes, but things like, do I want my priorities to be pedestrians having their wait times reduced, or do I want speeds reduced on the corridor? I can simply toggle switches in the dashboard and have these policies pushed out to the corridors, pushed out to the grids, or pushed together into the interlinked network of roadways and highways. Fundamentally also operating in this environment of safety constraints. So not to belittle the traffic signal controller, the modern traffic signal controller, but all these safety features are built in and were developed really over the last 50 years. So we're able to use the value that's in the infrastructure at the intersections, but also driving actions that are based upon the current situations and the policies that your traffic engineer and the practitioners want to have happen on the corridor itself. So taking all these inputs and letting the engine, the artificial intelligence engine, decide what decisions happen actually out at the traffic lights themselves. So let's take a look at some examples. So a typical scenario where it takes some thought process behind developing timing plans is, let's say, unidirectional coordination. So this would be a model where it's an AM peak perhaps, that the bedroom communities are going to some corporate center or some urban environment. And I have to make the decision of, I want traffic to progress, but I may want to reduce side street delay so that the really high volume, high density housing complex here doesn't get snarled and people complain and backs up through other intersections. So I have to immediately start thinking about, so what are my constraints? Do I have to stop traffic here? Then you have to go through this whole process of, well, do I need multiple timing plans? Do I have an AM peak? Does my AM peak start at 8 o'clock? Does it start at 7 o'clock? Is it different on Tuesdays or Fridays? Is it different on Saturday? So all the models, all the assumptions start to fall apart. We have high degrees of variability. Not impossible, can be done, but requires a lot of manual intervention. So again, we submit there's a better way to do this. So using AI-based sensors to gather this data about approaching and waiting vehicles, pedestrians, cars, or cyclists, and this balance then of having to make a compromise between side street delay and progression or in travel time goes away, because I can have this information sent to an optimization engine. That optimization engine can make decisions, sent to a traffic controller, again with all the safety constraints, and that there are no new timing plans required in this environment. So think about that. I no longer have to go through the laborious process of making counts, creating timing plans, going back and testing my fundamental assumptions. Technology exists now to do this, where the traffic practitioner can now focus on the really important things like safety and roadway improvements and gaining safety insights from the data that comes out of systems like this. So we get a little more complex, bidirectional coordination. So now if I want to balance progression along a corridor and reduce side street delay here, and maybe here, maybe you've got a big box store here, I've got a community here, and I've got a train station here, where the variability goes up and down. Where do I decide I have to start building my timing plan model? So I may have to create a breakpoint here. But if the volumes change here on the side streets, the fundamental assumptions start falling apart. So then I have to make this decision of, what is my compromise? Is my compromise reducing delay on these side streets or making progression happen on a corridor? So again, this traditional area of having to make compromises based upon the current state of the underlying technology driving traffic signals. And again, we submit that the best way to do this is use edge-based sensors to gather this data, feed that into an optimization engine, which can make the decisions as the smartest traffic engineer in the world, who's omniscient, can see everything, and is able to make decisions based upon previous learnings as well. Because here's the point of AI. It continually revises its models and revises its effectiveness. Outputs decisions as timing plans, if you will, an instantaneous timing plan to a traffic signal controller, and with no new timing plans. Now we start getting more complex, things like crossing arterials, where now I have several things I have to consider. Do I want to reduce side street delay? Do I want to move pedestrians more safely? This is an area where I have to make a decision. Well, if I can't effectively make timing plans here, do I have to push pedestrian crossings downstream of this crossing arterial because there's a potential safety issue? Do I have a fire station? Do I have a hospital? Will things be variable? This becomes a very complex environment to time for. So if I went out, did a live observation 2 months ago about traffic volumes, I guarantee you those assumptions are no longer valid now, particularly in this current situation. And prior to this current situation, it's really doubtful they're valid, because if there's variability, these models start falling apart. So again, we submit that use these intelligent sensors at the edge to capture data the way the world's brightest omniscient traffic engineer would, make decisions based upon the AI algorithms that run in the processor, an optimization engine, and drive signal decisions to the traffic signal, make the lights change according to the decisions made by the AI engine. And then again, of course, no new timing plan. So then you start stepping up degrees of complexity, types of networks that have been impossible really to time for with variability. So urban grids, there's a reason we haven't seen a lot of automation in urban grids, is because the math and the technology simply hasn't been available to do this without AI. So if you look at a typical urban grid environment where I may have arterials that cross, I may have one-way streets, I may have, let's say, a school that creates stops here, but then I also have to worry about, well, do I have queue length issues? Do I not want this traffic spilling through this traffic? Anybody who's been stuck in Manhattan at a rush hour knows, you don't want to block the box. That's a big ticket. So safety issues behind that. But if you start seeing the complexities and the permutations of timing plans needed to handle an environment like this, become virtually impossible to manage. So in many cases, agencies will make a best effort finding the least common denominator, which might be like a short cycle length to move pedestrians, or the other choices simply do nothing. And we submit there's a better way to do this using AI-based sensors and letting that real-time information go to an optimization engine, which drives decisions to change the lights and tells this controller sitting at the intersection, according to safety constraints, how to drive the lights according to my policy decisions with no new timing plans. Some environments, just from a math standpoint, become exceedingly difficult, if not impossible, for humans to handle, and completely impossible to handle in real time. So complex interdependencies like a grid network in one city that expands to another area where you've got other cities that are tied into highway segments, which may have a lot of variability in volume. If you look at current volume data, the variability there's no way of predicting how this is going to happen. And as the world comes back, comes back out of lockdown, what will this look like? Will there'll be an AM peak? Will there be a PM peak? Or with the origin destination models that we've used for the past 30 years have any relevance at all? Then you have more complexities like rail crossings. Rail crossings are extremely disruptive, obviously, because I lost capacity. That roadway simply cannot move. So having advanced knowledge about that I can start factoring in these issues that could potentially be areas of compromise in my timing plans. Then the unforeseen things like incidents. So if there's a highway closure or a turnpike closure and it dumps tons of volume on an arterial that was set to on a PM peak or a nighttime plan, how can I effectively deal with that? And typically in urban environments, there's usually a response to these incidents where you'll have a first responder, then you'll have fire EMS, then if it's a city that's using emergency vehicle preemption, those preemptions start locking up the entire network. So this very complex grid network starts not running very effectively and basically just stops. And it typically happens with larger scale incidents is that you'll have multiple responses. You may have another fire station here that stops this segment of the network and another responder that stops. And coming out of that preemption environment is a major challenge to deal with, because that's something that's unforeseen. The timing plan simply can't deal with. We submit AI is a better way to do this with, of course, no new timing plan. So let's revisit then a seemingly very simple potential compromise. Seemingly very simple, but actually devilishly difficult to time signals for is doing something called transit signal priority, where I want to run buses through an intersection very efficiently to make mass transit more appealing to users, more tolerable. And as you may have seen in the graph earlier, that ridership is down significantly. So most transit operators want to move buses more efficiently and more effectively to become a more attractive modality of transportation. But then the overall objective of the city or the agency could be to have pedestrians and bikes have priority, because bike usage is going up significantly, so is pedestrian usage. Actually, pedestrian usage in most of the areas that we've studied hasn't really changed at all, and it's actually going up. So it seems like a fairly simple environment, but a devilishly difficult thing to time for. So using AI, I can balance these competing priorities and equitably distribute green time by letting AI do this. And it requires no new timing plans to do that. So let's revisit this process flow again as prescribed by FHWA. So AI lets you take these assumptions in the manual process of gathering data and expecting that these assumptions may hold true. We give the ability to the traffic practitioner to focus on the really important things, or what are the objectives? Are the objectives safety? Are the objectives decreasing travel time? But able to make decisions without having to think about the built-in compromises of the old architecture. So following the process flow, confirming your standards and procedures, dividing the system into sections. This is part of it. So maybe I have an urban grid. I want to behave one way. And then maybe I have arterials that feed a grid where I want progression there because I don't have as much pedestrian traffic. Maybe I have a place where there's a rail crossing that I have to factor in, or a bike path that crosses. I don't have to think about compromises anymore. I can configure those, have multiple performance measures that I'm after, and set policy parameters in an AI-based system. So we're going to revisit this concept again of simulation. So using these deep learning AI techniques, the system is continuously evaluating what's going on hundreds of times a second. And the thought process is, in an AI-based system that manages traffic, is it thinks in terms of timing plans that are going to be used right now. So being able to calculate all the permutations of timing plans with every signal that's under control, you can see that simulation actually happen. That's much like what happens with the human brain. Is when you start thinking about something, a memory runs through a simulation. It's a stored plan in your head that's run through your biomass AI processor, and that's how you verify what's happening. So the same way in an AI-based traffic control system. So I simulate the operations and then monitoring it. So you'll be able to see what the performance is. And one of the major aspects of an AI-based system, it's continually learning about its environment and its outcome. So if my output is going to be reducing pedestrian wait time, I'll continue to revise for that priority. If my output's going to be creating better progression on the corridor, I'm continuously going to learn the best way to do that from a traffic plan perspective and how that applied, or preemptions or what have you. So in summary, the traditional strategies use historical data and assumptions about predictable, linear, gradual change. And those strategies are ineffective and been ineffective large shifts in variability and complex interdependencies. And particularly today, we have no idea how traffic is going to change. So does it make sense then to go back and go through this laborious process of trying to create manual timing plans based upon assumptions made at some point in the past about some future point when we have no reference point in the future? These potentially conflicting priorities are managed safely and effectively. So you can think about it eliminates the priorities. You determine then what is your policy, what's the level of priority given to a policy without having to deal with compromises. And AI-based systems, they eliminate these compromises and the need to retime traffic signals. And doing all this with no new traffic timing plans. At this point, I'll stop and see if we have any questions. And I'll ask Kel.
Hey, Tom, I think you did a really great job answering the questions preemptively. I don't see anything in the chat at the moment that needs to be addressed.
Great. Everyone, thank you so much for your participation. So this is the first in a series. Some future topics are going to be using AI and particularly really intelligent sensors to gain safety insights from signal assets. There'll be a segment on democratizing connected autonomous vehicle ecosystem with AI, really interesting topic. If there's anything else you'd like to see covered by us, my contact information is in this and on the slide. I'll also send an email update to you as well. If you have any suggestions for future comments or topics, it'd be most appreciated. Again, thank you very much for joining us today. I hope it was a good investment of time, and I hope that you all stay safe and otherwise well. Have a good day.